Hi, I'm Kathy. In this lesson, we're going to study exponential functions. Our specific objectives are linear and exponential growth, exponential models, compound interest, and the natural exponential function. Let's begin by comparing numerically a linear and an exponential function. Two tables are given. This first table represents a linear function, the second an exponential function. When looking at a table to determine if it's linear, first the x values need to increase by a constant amount. In this case, each x increases by 1. And if, when that is true, the y values or f of x values increase by a constant amount, the table is linear. In this case, the constant increase amount is 3 when the constant increase in x is 1. Also notice in this table that when x is 0, f of x is 5, and we can write a formula for this function in the form f of x equals 3x plus 5. Notice that that's the constant increase in f of x when x increases by 1, and this is the f of x value when x is 0. Now this is an exponential function given in table form. Notice that if we wanted it to be linear, the f of x values would have to increase by a constant amount, and they don't. What happens with the y values in this second table is that they increase by a constant factor. If I multiply 5 by 3, I get 15, and then 15 times 3 is 45, then 45 times 3 is 135, and so on. That's what makes this an exponential function. There's a common factor that is used to multiply by a particular f of x value to get the next f of x value. Also notice from this table that when x is 0, f of x is 5, and I can write this particular exponential function as 5 times 3 to the x power, where 5 is multiplied by this quantity. Notice that when x is 0, 3 to the x would be 1, and f of x would be 5. Well, let's look at a general formula for an exponential function. A function f represented by f of x equals c times a to the x, where a is positive, bigger than 0, and not equal to 1, and c is greater than 0, is an exponential function with base a. That a is the base in the exponential function. Here's some examples of exponential functions. Things like f of x equal 4 to the x, and in this particular exponential function, the base is 4. Here's another. G of x is negative 8 times 1.2 to the x. In this particular function, the base is 1.2. Here's a third. H of x is 5 times 3/4 to the x, and in this function, the base is 3/4. Well, that's what an exponential function looks like. Let's graph a couple of exponential functions on a calculator. Here are the two functions we're going to graph. We're going to graph 5.6 to the x power and 1/5 to the x power and compare the two. So let's go to our graphing calculator and enter 5.6 to the x power and then 1/5 to the x power. And as a window, let's use -3 to 3 with a scale of 1 in the x direction, -1 to 6 with the scale of 1 in the y direction, and push graph. The first function that graphs is 5.6 to the x. The second is 1/5 to the x. Notice that the 5.6 to the x with a base 5.6 from left to right grows. We call that exponential growth. The second function that graphed, the 1/5 to the x, got smaller from left to right. We call that exponential decay. Let's generalize those two graphs. First of all, if we graph the function y equal a to the x, where a is a number bigger than 1, remember a is the base, where the base is bigger than 1, we're going to get a graph roughly like this shape, and that's exponential growth. if we graph y equal a to the x, where a is a number between 0 and 1, remember the example of 1/5, we're going to get a shape roughly like this, which is called exponential decay. Well, let's continue graphing for a moment, but compare an exponential function to a polynomial function. Here's what we want to do. We want to compare f of x equal 3 to the x and g of x equal x cubed. This is a polynomial function. We want to compare them graphically for x greater than or equal to 0. So we need to go back to our calculator, clear out the functions that were there previously, and put in 3 to the x power, and we want to compare that to x to the 3rd power. Well, again, I want to set a particular window, so I do want to compare these just for x greater than or equal to 0. So I'm going to set x min to 0, and let's set x max to 12. And a scale for 1 in the x direction will be fine. Well, let's set y min to 0 and y max to 10,000. And we'll want to change our y scale to 1,000, and we're ready to graph. We'll see the exponential function and x cubed. X cubed is the lower graph, and comparing these, we'd say that 3 to the x grows much more rapidly than x cubed. We can kind of summarize that a little bit. An exponential function has a variable for an exponent, whereas a polynomial function has constant exponents. For example, and these are the two we just graphed, f of x is 3 to the x, represents an exponential function. Notice the variable is the exponent. G of x equal x cubed represents a polynomial function. Notice the constant exponent. And remember from the graph that the exponential function grew quite a bit more rapidly than the polynomial function. Well, let's continue with exponential functions and look at some different kinds of models. Here's the first one. If a radioactive sample containing C units has a half-life of k years, then the amount A remaining after x years is given by A of x equals C times 1/2 to the x over k power. Remember, k is the half-life. C is the initial amount of the sample, or the amount of the sample, and x is the number of years after which A remains. Let's try an example. The half-life of carbon-14 is approximately 5,700 years. How much of a sample of 3.8 grams will remain after 12,000 years? Well, we want to know what is A. When we start with 3.8 grams, so that'll go in for C in our model. The base of this half-life model is 1/2, and the exponent should be x over k, where x is the number of years, 12,000, and k is the half-life, which is 5,700. And so using a calculator, I'll get a number for this. Let's go to our calculator. What we want to find is 3.8 times 1/2 to the, and now I'm going to use parentheses around my exponent because I have a division within the exponent, 12,000 divided by 5,700. I get a number 0.883, etc. I can say that A is approximately 0.88 grams. So after 12,000 years, if I start with 3.8 grams, I'll have about 0.88 grams. This seems like a reasonable answer. The half-life is 5,700. That's the amount of time over which exactly half will decay. 12,000 is very close to 2 half-lives for this particular carbon-14. Well, I'd like you to try a problem like that. Here's what I want you to try. The half-life of radium-226 is 1,620 years. How much of an initial sample of 3.4 grams will remain after 2,000 years? Stop the tape and try this one, and when you're done, restart the tape to check your work. Well, let's see how you did. Here's our model. We want to know the amount remaining, A. If we start with an initial amount of 3.4 grams, and let's see, 2,000 years are going to pass, and the half-life of radium-226 is 1,620. Let's put that into our calculator. We have 3.4 times 1 divided by 2. It's not a division symbol. All of that to the parentheses 2,000 divided by 1,620. And we end up with 1.4448, etc. We can say that A is approximately 1.44 grams. So after 2,000 years, if we start with 3.4 grams of this substance, this radium-226, 1.44 grams will remain. Well, let's look at another kind of exponential model. This one involves interest. If A sub $0 is deposited in an account paying an annual rate of interest R, compounded m times per year, then after n years, the account will contain A sub n dollars, where A sub n is A sub 0 times 1 plus R over m to the m times n power. Notice in the formula, A sub 0 is the amount we deposit, R is the annual rate of interest, m is the number of times the interest is compounded per year, and n is the number of years we're going to keep the money deposited. Let's try an example involving this formula. In fiscal year 1996, the federal budget deficit was $107.3 billion. At the same time, 30-year Treasury bonds were paying 6.83% interest. Suppose the American taxpayer loaned $107.3 billion to the federal government at 6.83% compounded annually. If the federal government waited 30 years to pay the entire amount back, including the interest, how much would this be? Well, let's think about this. We have this formula. The way that the problem's written, it's as if we're looking for A sub 30. That's probably the best place to start because we're going to keep the money for 30 years, or the government actually waits 30 years to pay the money back. The amount of money is 107, that's not very clear. A sub 30 is 107.3 billion. We have to keep in mind that our money is in billion. Our interest rate is 6.83%. Now I need to use that as a decimal, 0.0683. And we're going to compound that annually, so m is 1. And again, the number of years, let me put 1 for m, the number of years is 30. We can pick up a calculator and get a number again. So on our calculator, we'll do 107.3 times 1 plus 0.0683 divided by 1, which I'm not going to enter in the calculator. And I'll raise that to the 30th power. Looks like that number is 778.75 if we were to round. So let's write that A30 is approximately 778.75. Now we need to interpret our answer. This means that the government would owe $778.75 billion. Well, let's continue our discussion of exponential functions and look at a particular base of interest. This one's called the natural exponential function. The function f represented by f of x equal e to the x is called the natural exponential function. The number e, which notice is the base in the function, is an irrational number approximately equal to 2.718. That doesn't mean that is it exactly, it's approximately this. Well, let's practice with the number e and a calculator for a moment. Using a calculator, let's find a couple of values. On our calculator keypad, we'll have to push second and the button that has e behind it. and put in a 2 to find e squared. That number's about 7.389 and so forth. The other calculation we want to make is e to the negative 1, and that number's about 0.36787. So we could say e squared is approximately 7.389, and e to the negative 1 is approximately 0.368 if we were to round. Well, let's try an exponential model that involves this base e. Here's what we're going to do. At an intersection, cars arrive randomly with an average weight of 30 cars every 45 minutes. The likelihood or probability that at least one car will enter the intersection within a period of x minutes can be estimated by f of x equals 1 minus e to the negative 0.75x. So for this model, x is a number of minutes, and f of x is the probability that at least one car will enter the intersection over that time period. So the first thing we want to do with this model is find the likelihood, the probability, that one car enters the intersection during a 5-minute period. Well, here's that problem rewritten. What that really means we want to do is take our model, let me write the model down, 1 minus e to the negative 0.75x, and evaluate it at 5. So find f of 5. 1 minus e to the negative 0.75 times 5 is the number we're interested in finding. So again, let's use a calculator. And on our calculator, we want to find 1 minus, choose your e, to the negative 0.75 times 5 power. And notice that the whole power on e is in parentheses. Pushing enter, I get a number that looks like 0.976 if we were to round. So I can say f of 5 is pretty close to 0.976. Remember that f is the probability that at least one car enters the intersection over a 5-minute interval. So we'll say that there's a 97.6% probability that a car will enter the intersection on a 5-minute interval. Well, continuing with this model, let's try another question. Here's what we want to do. We want to graphically determine the value of x that gives a 50-50 chance of at least one car entering the intersection during an interval of x minutes. Well, we better remember what our model is. 1 minus e to the negative 0.75x. And we want to answer the question graphically. That's our direction. So we're going to go to a graphing calculator and graph this function. We'll put in 1 minus e to the negative 0.75x. We want to graph that. Let's set an appropriate window. Let's set x from 0 to 20 with a scale of 1. And let's set y from 0 to 1.1 with a scale of something small, like 0.1. Let me push graph and see how that model looks. Now the question is to graphically determine the x that gives us a 50-50 chance of at least one car entering the intersection. So what I'm interested in is what is x when y is 0.5, or a 50% probability. Let me start with my trace key and move it with my arrow key, my arrow button I should say, until x is close, until y is close to 0.5. Need to do some moving here. 0.6, 0.5, 0.47. I'm going to leave my trace key there and zoom in on that point and see if I can refine this estimate just a little bit. So I'll choose zoom 2. Recall that when you zoom in, nothing happens until you push the enter button. And I'll get that little portion of the screen zoomed in on. Push the trace button to have your cursor go back to the curve. And I'm going to move my trace cursor just a little bit. And I get pretty close to 0.5 there. I'm in zoom in mode, so I can push enter one more time. I can push it as many times as I want, but I'm going to push it one more time. Again, select trace, and I can see that the x value is about 0.957 when the y value is close to 0.5. Is it 0.957? Yeah, between 0.95 and 0.90. Let's go between those two values and say that x is about 0.92, somewhere between 0.90 and 0.95 minutes. So over the course of 0.92 minutes, there's a 50% or a 50-50 chance of at least one car entering the intersection. Well, in this lesson, we did a number of things with exponential functions. Be sure to work lots of exercises from your textbook for practice.